Thank you, Peter. Good afternoon, everyone. First of all, I would like to thank the organizer to give me such a chance to report you our recent progress on ion beam plasma interaction. So the title is Energy Deposition and Excitation of Wakefield in case ion beam pass through a plasma target. Currently, I'm in Yongtao University, and I'm also a part-time in Institute of Modern Physics, Lanzhou. Here shows the main collaborators from Dalian University of Technique and also from ETAP, Technique University of Darmstadt, and also Frankfurt University. This is the outline of my talk. First, the background and motivation. So the energy deposition and transportation of ion beam in plasma is a very important topic. For example, for the alpha heating in ICF fuel or fast ignition of a fuel with ion beam, and it's also important to in case of generate high density with heavy ion beam, since the heavy ion beam for sure will have a long duration than a laser. So we also interested in the laser Wakefield self-modification. So this is for the Wakefield. Maybe we are familiar with the laser drive Wakefield or fast electron. But for a proton beam or ion beam to drive a Wakefield, so there's no such experimental result, First, let's go a little bit detail to the energy deposition in ion of ion in plasma. So we know there's a large difference between different theories, especially when the ion energy is lower or middle. So that means the velocity of projectile is in order of the same velocity of the plasma. So these two figures shows the velocity and the energy deposition, energy losing certain power. So we see when the velocity is closer, then there's a big difference between different theoretics, and here also just shows the same case. And as we know, in the annual report of NIF 2012, it said even the goal of demonstrating the alpha heating is still challenging. And there are still a little of experiment data, and the experiment data is also different, has a big gap with different theories. So, for example, this is the experiment in 1990s. So we see the energy. This the red line, the red point is the experiment data, where use some 100 keV heavy ion passing through a hydrogen plasma, and this merit, and it's of course several around 30 or 40 times higher than if comparing to the energy loss in cooled gas, and the theory cannot predict very precisely. And this experiment was done in the GSI, so they use laser to produce intense plasma. But to achieve low energy heavy ion beam, they use energy absorber to produce around 5 MeV carbon. So the blue point is the experimented, and the lines are different theoretical value. So we see the energy loss in plasma So the experimental data is much lower than the theoretical calculations, especially so for the low energy region. And the other point, the transportation of ion beam in plasma. So we know the plasma lens effect. So it was already reported by several speakers, and we also know the Wakefield self-modification. So the awake projection at CERN. So they use 400 GeV protein to passing through a 10-meter plasma, and the theoretical predict the proton beam will be cut to pieces due to the Wakefield oscillation of the Wakefield, and they put some electrons inside. Such a Wakefield can accelerate the electron beam to few 100 MeV, even to GeV region. But there's still lack of experimental data on protein-driven or ion-driven Wakefield self-modulation instability. So this now this shows the experiment setup. Here we use a gas discharge, and in the middle we set high voltage in range of 2 kV, 2 kilovolt to 5 kilovolt, and both sides is grounded, and so the plasma will produce in both sides, and in that case the plasma will be more uniform, and the influence to the ion beam will be lower than you discharge in one side. So such a device can produce a plasma in lifetime of microseconds, and the density of the plasma is around 10 to 16 or to 10 to 17 per cubic centimeter, and the temperature is around 2 electron volt. It's not fully ionized, so there's already some measurement with we measured the liner electric density and also the liner atomic density use laser interferometer. So this shows the liner atomic density after discharging. So this is the time of discharging, and this is the density. So after discharging, the gas inside will go out, and so the density will go down. At the same time, due to the energy deposited into the gas, so there's free electron density is going up to the maximum at around 3 microseconds or 4 microseconds, and then go back again. And after we add such a plasma target in our beam line, and this is beam direction. And after beam passing through the plasma target, we put a bendium magnet, so 45 degree, and we put a position sensitive detector, and this detector has a very good space resolution, and also has a very sharp gate. So the gate can be even less than 10 nanoseconds. Such a bendium magnet with such a detector, we can get the energy resolution around 1 electron volt. And the experiment was carried out at MP Lanzhou. So the beam with proton to uranium, and with energy ranging from 10 to 300 keV is available there. And with this setup, we would like to study the effect of initial kinetic energy or initial charge state or nuclear charge on the energy loss. So this figure shows the result. since we have bend magnet, this is the position or the beam after the bend magnet, and this is the beam after a certain time, after discharging. For example, this is the 200 at 200 nanosecond. We open the detector for 1 or 200 nanosecond and collect for several times. We see the beam. This is the beam position, and it reflects the energy. So we plot the energy as a function of the discharging time. Here shows the picture. The black point is the data take from here. You see, and from the result we found the energy loss was enhanced by a factor around 4 or 3.7 if comparing to a same amount of gas, and the black dash is the calculated values. So we see so the theoretic value fit very well with the experiment data if we use proton beam. However, when we use helium ion, we use 400 keV helium ions, helium 2 plus, and so it's also 100 keV per nuclear. And then we have also some other data, and this just like example. So it's have the same means. This include gas, and this is the data after certain discharging. So this plot the energy loss as a function of time after discharging, and the black point is the experiment data, and this is the three I think very formally used code or theoretic value. We see the measured data is obviously lower than what we observed. Then the experiment data is much lower than all the theoretical value, and we take the Bis function. This is the Bis function, and if we take the Z effect equals 1.73, so we found the experiment data, the theoretic prediction will be fit very well with the experiment data. So this effective charge is just from the experiment data. And if we look into some equilibrium charge state, take some formula. This is much lower than the formula. The formula, if we use plasma target, the equilibrium charge state will be 1.85 or around that value. So this is experiment data. So much for the energy loss, and this we also found. For example, here we see on the detector there's very small point when the plasma electron density reaches the maximum, and we also observe such effect when we use 200 keV proton, and there's a lot of focus point, and this focus point is much smaller than the beam in a cooled gas or in a vacuum. So on the other hand, we found when the beam was focused, the energy of the beam is very uniform. So this is on the same line. So the energy is very uniform. So we did some peak simulation. So this data was already shown several times. We simulated years ago, and this is the radial electric field after a beam passing through, so for 200 keV, passing through a fully ionized plasma. And this the longitude electron field, we see the oscillation of the weak field. And under such a weak field, so the beam will be bunched or cut to several bunches. And in this, we can see the plasma can form a self-modulated and periodic or focusing tunnel. And just very recently, we also did a simulation, use another simulation group that they do the simulation, and we want to see how about the electron profile, the background electron profile, and comparing to that the electron, the beam profile. So the up finger is the electron density in the plasma. So after a certain time, we find along the trajectory, the electron was focused, and at the same time, the beam, the heavy beam, the proton beam is also focused. And in the very beginning, we think maybe the electron and the proton will be separated. Finally, we found it's not the case. So the electron, this here is the proton, and it's just a little bit after the electron beam. And such electron beam move closely behind the weak field, which is excited by the proton beam. And this electron beam will be accelerated as the same velocity of the proton beam. So in that case, the collision, the Coulomb collision between the ion and the free electron will be reduced. That's why the electron stopping can be neglected after the weak field is built. Now, too fast. Come to the near future. So last year we get funding, and we would like to build such a new or such device. So for example, we are built a faster scan field, so that we can scan this beam, and the beam can be scanned to different points. That means we can get the time profile of the beam after passing through the plasma. And we also use new plasma device. Maybe we will use the radio frequency plasma or the metal plasma. So we use some laser to heating on the lithium metal gas to get a plasma condition. Maybe similar to the what CERN done. CERN is going to do, and we also would like to use laser ion source so that we can get some very short ion bunch and to see the weak field effect with such short bunches. So now come to the summary. For energy loss experiment, we observed enhanced energy loss after passing through a plasma if comparing to the neutral gas. And for proton, the experimental result fit well with the theoretical calculations. But for helium, we found most of the theoretical calculation overestimate the energy loss. And if we take an effective charge of 1.3, 1.7, it will be fit well. in base calculations. And so the Wakefield self-modification in case of proton beam passing through a plasma, I think was firstly observed in experiment, and we found very strong focusing effect where after such a Wakefield build, the energy of the focused beam will be very uniform. And the peak simulation suggests that the Wakefield can form a self-modulated, periodic, and focusing and also collision-less tuner. With the chance, I thank the support from our collaborator again, and thank you for your attention.
Questions?
Oh, yes. Okay, very clever presentation. Yeah. Very nice presentation, but you said that with this Wakefield device, you suppress electron contribution to the proton stopping. But what about the ion contribution to the proton stopping?
What about ion collision?
Ion, yes.
So the electron stopping, I think, is the dominant the energy loss.
It depends the velocity range.
Depend on the velocity. And if you know, now we are using 100 keV or more, so in such energy region, so the ion energy loss will be much lower compared to electron. Yeah, that's so we did the calculations. This is 1 order lower than electron contribution.
You have found the anomalous enhancement of stopping power at low values of ion beams. What is the physical mechanism?
Good question. You know, in this base calculation or other calculations, so the energy loss maybe we can cut to several parts. The energy loss due to the collision with the bound electron, free electron, and also ion collisions. And so the main parameter is the logarithm of C. So this value, and if we comparing the average ionic energy to the energy of plasma. So this value, we compare to this logarithm data. This is much higher than this one. So that's the most. That's the reason why the energy loss in plasma is much higher than it in the cooled gas. So the logarithm this is the main reason.
Yeah, I would like to thank again for a nice talk. My question related to this slide as well. I remember in a recent workshop in Moscow, Professor Hoffman also reported about similar results,
yeah.
And he showing it's very nice, interesting results. And my question is, have you published this? So I mean, as a theoretician, for us, it's very interesting to analyze such anomalous effects.
So till now, I have not published this data.
Yeah, I couldn't find the similar. So, are you planning or?
I'm planning. Yeah, just of course, we planning to publish.
Or we'd like to make some calculations.
Yeah. We want to, you know, for example, we want to find out how to determine the effective charge. Use some formula. So that's some formula for example, for the equilibrium charge state. But the equilibrium charge state in this case will be 1.85. It's higher than the experiment did, and the equilibrium charge state in a cooled gas in this case will be 1.4. Yeah, that means this still I think we still need some work to do. And for experiment, we also want to observe how much N was changed to helium-1 plus. I'm not sure if I have in this region we can only see the helium-2 plus, and if we move the magnetic window, we can also observe helium-1 plus, and we want to do some measurements to compare the ratio of two charge states. That's the experiment.
Just last remark is that this effective charge theory, it's kind of semi-empirical, so it would be very nice to see more constructive theory which can give answer why it's coming.
Okay, we can discuss it.
Okay, very nice talk. I mean, I was wondering what's the size of the beam, longitudinal, the size of the beam, because I mean, unless the beam, because it's very difficult to excite the self-modulation instability in Wakefield generation unless you have very sharp edges of the beam. So I'm curious about longitudinal distribution of your proton ion beam.
In simulation or in experiment, we use continuous beam, not a path beam. And we find that even you use a continuous beam after a certain distance, here, I think from here is 4 centimeter away from the entrance. Yeah. So that means after 4 centimeter, the beam will be passed. And in the very beginning, there's no such effect. Only after a certain time, we can see the oscillation of the Wakefield. That's
what is the particle energy?
200 keV here we use in the simulation. And in experiment we do several energy. It's just to sample.
All right. Very, very good discussion. Thank you very much, Yongtao.
Thank you. Thank you all.